This is the first video in a series of lectures about gauge theory and renormalization group equations related to model building in high-energy physics. We're going to start today just talking about the U1 gauge case because that's the simplest case. So we can write down a general U1 gauge theory. Start with just one fermion with a charge q, psi, and a complex scalar, its own respective charge phi. You can write the Lagrangian down like this. Have each of the following terms, as we have the kinetic terms for the gauge bosons. We have the Fermi kinetic term, we have the scalar kinetic term, and their respective masses. Now these D's are covariant derivatives. Look very similar for the U1 case because the only difference is the respective charge associated with the gauge boson. Now G here denotes the gauge coupling, and it's related in QED, for example, to the electric charge by the fermion's charge. This is the charge under the representation, not its actual electric charge. So the electric charge is related to the gauge charge times the gauge coupling, QED. Now the process to do is first we want to renormalize all the fields and couplings by calculating their loop corrections. With the couplings, we can actually derive the renormalization group equation. So in this case, we're just talking about the gauge coupling in the mass terms. We don't have any fermion-scalar interactions at the moment. Now, when we figure this out, it'll tell us how the couplings scale with energy. And this is because the couplings are the actual measurable quantities. At a particle collider, your cross sections and amplitudes, everything is related to the gauge coupling, to the mass terms. And if you do have a theory that has interaction terms between the various fields themselves, you will measure those as well. Yukawa is an example. Before we want to go further into a generalized U1, do the process for QED with one electron, because in doing those loop corrections, we will see some similarities in the actual loop calculations to our general case, and if we do it for this case, we might be able to reuse some of our loop processes, our loop calculations for future use. So the 0th order Baire, or also known as the Baire-Lagrangian for QED, is this. Now I've explicitly written out the covariant derivative to just be the pure kinetic term plus the gauge interaction term. And then we have some mass. Now these are known as the Baire coefficients, this E here and this M here. These are not the physical ones we measure. These Baire ones are hidden behind all the loop corrections. So what we do is we write down the Phi diagrams for each term. So we have the kinetic energy for gauge bosons, kinetic energy for the fermions, the gauge interaction between the gauge bosons and the fermions, and the mass term. So that should be just 1 power of m. Now, first what we're going to do is we're going to calculate the renormalization of the photon wave function. And so we have the tree level, and then we have the one loop. And in our theory, in the QED, there is only one loop correction with one fermion, and that's due to the fermion running the loop. And this is, think about it, each of these vertex here are just the I, G, Q, gamma, mu. And so each term gets one of those. That's just the couplings in front of each of the interaction terms. And we use the Feynman to calculate this integral as such. Now, it's often denoted as capital pi, I pi uv, and the 2 here denotes the fact that this is going to be second order in E. The overall negative comes from the fact that this is a fermion loop, as well as the trace term comes from it's a fermion loop. So as we move forward, we just the slash notation to the numerator. Because remember, the slash notation this is actually k mu gamma mu, or obviously not the mu because we use that, but a different one like rho. And so as we expand out and do our proper algebra for all the gammas, we get this. Now, what we want to do is we want to rearrange the denominator, because this integral is over k, which is the loop momentum here. We want to get all terms of k together, because q is more or less it's constant. It's the external momentum that comes in to the loop, and so it should be the same external momentum that exits the loop. And so we're not really worried about integrating over q here. So what we can do is we can use this Feynman parameters here, where we just introduce, this is a very common trick, and we just do a shift of our k to L, and then we say delta is just the non-k terms, or the non-L terms, I'm sorry. And so the denominator reduces to just simply this. Now we'll come back later to that, but it's easily seen. The rest of the terms in the numerator shift. So before we go any further, we want to do a simple Wick rotation, and this will help us because it's going to take the Minkowski metric and change it to a Euclidean metric by doing a Wick rotation on the 0th component. So we're actually only interested in terms, the non-finite ones. Those are the terms of interest for us in this renormalization group equation process. And so when we get the finites, we can kind of put those to the side and not worry about those. Also, the numerator terms odd and L are going to be 0. That's just due to symmetry calculus, one like even odd symmetry of a function. So first and foremost is we have a possible quadratic divergence. And so the quadratic divergence terms from the numerator are these terms. And so what we want to do here is we can't use regulators, because no matter what, if the regulator we choose will obviously still give us quadratic divergence. And so the choice that we want to do to try and figure out this integral is actually dimensional regularization, where we move to, instead of 4 dimensions, we move to an arbitrary d dimensions. And so our identity relationship changes to this. So we move through, and we do here. Note, this is still going to be proportional. This still should obey the Ward identity in any arbitrary dimension. And we'll see that at the end. So here's some useful formulas. And for this one, we're going to use this, but let's see what happens. This actually changes to that. And this is due to the fact that we have this d term here. So this, what happens is we're actually saved by basically the gauge symmetry. This prevents us from having quadratic divergence. Now, this is due to the fact that we have this d term here that distributes, and then not just that is what's going to happen is it's going to take an extra factor of delta and move it up here. That's what's get rid of the negative 1. So this thing right here looks like this one for the case where there's no L's in the numerator. This is important for the next step in the calculation, which is the rest of the terms in the numerator that have no dependence on L. And so we can rearrange going through, we can get this term here. This is what it simply reduces down. So this is the only structure, and you can see that if you do indeed do the Ward identity, which is multiplying by an overall Q, this term should vanish. Right? So if I multiply everything by Q mu, multiply Q mu, the left side, and the same thing here, this entire equation, Q mu, everything should vanish, which take a moment to do this on your own time, it should vanish. And so what we can do here is actually extract the scalar from the tensor quantity. And so the tensor quantity is just, again, that term. And so what we have left over is everything else but that. And so what we're going to do is we're going to make a shift to a small parameter epsilon, which is going to approach 0 as d approaches 4 dimensions, and all the terms come out to be this. So we let that approach, d approach 4, epsilon approach 0, and we do the expansion about 0 or a small quantity, and we see that as d approaches 4, gamma approaches 4, we get gamma approaches, gamma of x approaches 0, we get this term as coefficient times a 1 over epsilon, which would be in pole as epsilon goes to 0. And so this is actually the term we're interested in. We're not really interested in finite terms here. And so again, take q to 0 because again we have no q dependence here. So if we actually take all loop corrections together, that would just be big pi without any 2 in the subscript, which is all possible. This should actually be 0 based on the way we set. So this is actually like an initial condition, a boundary condition. So just the second order one gives us this. And so we're actually only interested in this. So this is going to be a point of interest for future calculations, and we'll see why. So what is the significance of this? And so if we just focus on, one loop or second order in E, we can do a rescaling of all fields, where Z is actually from the entire loop integral, and so since the loop integral has two external A's, two external gauge bosons, each gauge boson gets a root Z, so that together the entire loop is just Z to the 1. And we can rewrite Z as the tree plus some correction, plus some delta, and so this contains all loop corrections. And so we'll actually be discussing in the next video how we're going to do for the fermion loop and then the vertex corrections. And then from there we'll go on to generalizing this and including scalars into our thing, because we have not done a scalar loop.